An alloy is a mixture of metals or a mixture of a metal and another element. Alloys are defined by metallic bonding character. An alloy may be a solid solution of metal elements or a mixture of metallic phases. Intermetallic compounds or alloys with a defined stoichiometry and crystal structure. Zintal phases are also sometimes considered alloys depending on bond types. Alloys are used in a wide variety of applications. In some cases, a combination of metals may reduce the overall cost of the material while preserving important properties. In other cases, the combination of metals imparts synergistic properties to the constituent metal elements such as corrosion resistance or mechanical strength. Examples of alloys are steel, solder, brass, pewter, duralumin, phosphor, bronze, and amalgams. The alloy constituents are usually measured by mass. Alloys are usually classified as substitutional or interstitial alloys, depending on the atomic arrangement that forms the alloy. They can be further classified as homogeneous, or heterogeneous or intermetallic. Introduction. An alloy is a mixture of either pure or fairly pure chemical elements, which forms an impure substance that retains the characteristics of a metal. An alloy is distinct from an impure metal, such as wrought iron, in that, with an alloy, the added impurities are usually desirable and will typically have some useful benefit. Alloys are made by mixing two or more elements, at least one of which being a metal. This is usually called the primary metal or the base metal, and the name of this metal may also be the name of the alloy. The other constituents may or may not be metals, but, when mixed with the molten base, they will be soluble, dissolving into the mixture. When the alloy cools and solidifies, its mechanical properties will often be quite different from those of its individual constituents. A metal that is normally very soft and malleable, such as aluminium, can be altered by alloying it with another soft metal, like copper. Although both metals are very soft and ductile, the resulting aluminium alloy will be much harder and stronger. Adding a small amount of non-metallic carbon to iron produces an alloy called steel. Due to its very high strength and toughness, and its ability to be greatly altered by heat treatment, steel is one of the most common alloys in modern use. By adding chromium to steel, its resistance to corrosion can be enhanced, creating stainless steel, while adding silicon will alter its electrical characteristics, producing silicon steel. Although the elements usually must be soluble in the liquid state, they may not always be soluble in the solid state. If the metals remain soluble when solid, the alloy forms a solid solution, becoming a homogeneous structure consisting of identical crystals, called a phase. If the mixture cools and the constituents become insoluble, they may separate to form two or more different types of crystals, creating a heterogeneous microstructure of different phases. However, in other alloys, the insoluble elements may not separate until after crystallization occurs. These alloys are called intermetallic alloys because, if cooled very quickly, they first crystallize as a homogeneous phase, but they are supersaturated with the secondary constituents. As time passes, the atoms of these supersaturated alloys separate within the crystals, forming intermetallic phases that serve to reinforce the crystals internally. Some alloys occur naturally, such as electrum, which is an alloy that is native to Earth, consisting of silver and gold. Meteorites are sometimes made of naturally occurring alloys of iron and nickel, but are not native to the Earth. One of the first alloys made by humans was bronze, which is made by mixing the metals tin and copper. Bronze was an extremely useful alloy to the ancients, because it is much stronger and harder than either of its components. Steel was another common alloy. Other ancient alloys include pewter, brass and pig iron. In the modern age, steel can be created in many forms. Carbon steel can be made by varying only the carbon content, producing soft alloys like mild steel or hard alloys like spring steel. Alloy steels can be made by adding other elements, such as molybdenum, vanadium or nickel, resulting in alloys such as high-speed steel or tool steel. Small amounts of manganese are usually alloyed with most modern steels because of its ability to remove unwanted impurities, like phosphorus, sulfur and oxygen, which can have detrimental effects on the alloy. However, most alloys were not created until the 1900s, such as various aluminium, titanium, nickel, and magnesium alloys. Some modern superalloys, such as Incalloy, Inconel, and Hastalloy, may consist of a multitude of different components. Terminology. The term alloy is used to describe a mixture of atoms in which the primary constituent is a metal. The primary metal is called the base, the matrix, or the solvent. The secondary constituents are often called solutes. If there is a mixture of only two types of atoms, not counting impurities, such as a copper-nickel alloy, then it is called a binary alloy. If there are three types of atoms forming the mixture, such as iron, nickel and chromium, then it is called a ternary alloy. An alloy with four constituents is a quaternary alloy, while a five-part alloy is termed a quinary alloy. Because the percentage of each constituent can be varied with any mixture, the entire range of possible variations is called a system. In this respect, all of the various forms of an alloy containing only two constituents, like iron and carbon, is called a binary system, while all of the alloy combinations possible with a ternary alloy, such as alloys of iron, carbon and chromium, is called a ternary system. Although an alloy is technically an impure metal, when referring to alloys, the term impurities usually denotes those elements which are not desired. These impurities are often found in the base metals or the solutes, but they may also be introduced during the alloying process. For instance, sulfur is a common impurity in steel. Sulfur combines readily with iron to form iron sulfide, which is very brittle, creating weak spots in the steel. Lithium, sodium and calcium are common impurities in aluminium alloys, which can have adverse effects on the structural integrity of castings. Oxygen, present in the air, readily combines with most metals to form metal oxides, especially at higher temperatures encountered during alloying. Great care is often taken during the alloying process to remove excess impurities, using fluxes, chemical additives, or other methods of extractive metallurgy. In practice, some alloys are used so predominantly with respect to their base metals that the name of the primary constituent is also used as the name of the alloy. For example, 14-karat gold is an alloy of gold with other elements. Similarly, the silver used in jewelry and the aluminium used as a structural building material are also alloys. The term alloy is sometimes used in everyday speech as a synonym for a particular alloy. For example, automobile wheels made of an aluminium alloy are commonly referred to as simply alloy wheels, although in point of fact steels and most other metals in practical use are also alloys. Steel is such a common alloy that many items made from it, like wheels, barrels, or girders, are simply referred to by the name of the item, assuming it is made of steel. When made from other materials, they are typically specified as such. Theory. Alloying a metal is done by combining it with one or more other metals or non-metals that often enhance its properties. For example, steel is stronger than iron, its primary element. The electrical and thermal conductivity of alloys is usually lower than that of the pure metals. The physical properties, such as density, reactivity, Young's modulus of an alloy may not differ greatly from those of its elements. But engineering properties such as tensile strength and shear strength may be substantially different from those of the constituent materials. This is sometimes a result of the sizes of the atoms in the alloy, because larger atoms exert a compressive force on neighboring atoms, and smaller atoms exert a tensile force on their neighbors, helping the alloy resist deformation. Sometimes alloys may exhibit marked differences in behavior even when small amounts of one element are present. For example, impurities in semiconducting ferromagnetic alloys lead to different properties, as first predicted by White, Hogan, Sewell, T. and Abri and Nakamura. Some alloys are made by melting and mixing two or more metals. Bronze, an alloy of copper and tin, was the first alloy discovered. During the prehistoric period now known as the Bronze Age, it was harder than pure copper and originally used to make tools and weapons, but was later superseded by metals and alloys with better properties. In later times, bronze has been used for ornaments, bells, statues, and bearings. Brass is an alloy made from copper and zinc. Unlike pure metals, most alloys do not have a single melting point, but a melting range in which the material is a mixture of solid and liquid phases. The temperature at which melting begins is called the solidus, and the temperature when melting is just complete is called the liquidus. However, for many alloys there is a particular proportion of constituents, either a eutectic mixture or a peritectic composition, which gives the alloy a unique melting point. Heat-treatable alloys. Alloys are often made to alter the mechanical properties of the base metal, to induce hardness, toughness, ductility, or other desired properties. Most metals and alloys can be work-hardened by creating defects in their crystal structure. These defects are created during plastic deformation, such as hammering or bending, and are permanent unless the metal is recrystallized. However, some alloys can also have their properties altered by heat treatment. Nearly all metals can be softened by annealing, which recrystallizes the alloy and repairs the defects. But not as many can be hardened by controlled heating and cooling. Many alloys of aluminium, copper, magnesium, titanium, and nickel can be strengthened to some degree by some method of heat treatment. But few respond to this to the same degree that steel does. At a certain temperature, and 1600 degrees Fahrenheit, depending on carbon content, the base metal of steel undergoes a change in the arrangement of the atoms in its crystal matrix, called allotropy. This allows the small carbon atoms to enter the interstices of the iron crystal, diffusing into the iron matrix. When this happens, the carbon atoms are said to be in solution, or mixed with the iron, forming a single, homogeneous, crystalline phase called austenite. If the steel is cooled slowly, the iron will gradually change into its low-temperature allotrope. When this happens, the carbon atoms will no longer be soluble with the iron, and will be forced to precipitate out of solution, nucleating into the spaces between the crystals. The steel then becomes heterogeneous, being formed of two phases, the carbon phase cementite, and ferrite. This type of heat treatment produces steel that is rather soft and bendable. However, if the steel is cooled quickly, the carbon atoms will not have time to precipitate. When rapidly cooled, a diffusionless transformation occurs, in which the carbon atoms become trapped in solution. This causes the iron crystals to deform intrinsically when the crystal structure tries to change to its low-temperature state, making it very hard and brittle. Conversely, most heat-treatable alloys are precipitation-hardening alloys, which produce the opposite effects that steel does. When heated to form a solution and then cooled quickly, these alloys become much softer than normal during the diffusionless transformation, and then harden as they age. The solutes in these alloys will precipitate over time, forming intermetallic phases, which are difficult to discern from the base metal. Unlike steel, in which the solid solution separates to form different crystal phases, precipitation hardening alloys separate to form different phases within the same crystal. These intermetallic alloys appear homogeneous in crystal structure, but tend to behave heterogeneous, becoming hard and somewhat brittle. Substitutional and interstitial alloys. When a molten metal is mixed with another substance, there are two mechanisms that can cause an alloy to form. called atom exchange, and the interstitial mechanism. The relative size of each element in the mix plays a primary role in determining which mechanism will occur. When the atoms are relatively similar in size, the atom exchange method usually happens, where some of the atoms composing the metallic crystals are substituted with atoms of the other constituent. This is called a substitutional alloy. Examples of substitutional alloys include bronze and brass, in which some of the copper atoms are substituted with either tin or zinc atoms. With the interstitial mechanism, one atom is usually much smaller than the other, so cannot successfully replace an atom in the crystals of the base metal. The smaller atoms become trapped in the spaces between the atoms in the crystal matrix, called the interstices. This is referred to as an interstitial alloy. Steel is an example of an interstitial alloy, because the very small carbon atoms fit into interstices of the iron matrix. Stainless steel is an example of a combination of interstitial and substitutional alloys, because the carbon atoms fit into the interstices, but some of the iron atoms are replaced with nickel and chromium atoms.